Hi, we got to talk about coal. Um, Coal, whenever you hear coal, you should think of electricity. For years now, coal has been the primary source of electricity worldwide. And um, whenever you're thinking of electricity and electricity development and somebody has electricity, chances are that they're talking about coal. So coal and electricity are basically synonymous. We are starting to find other sources of electricity, and coal does have a few other uses, but basically it's the same thing. Um, it's the most abundant worldwide. There's maybe 200 years of coal left on the planet. And I'm just saying, I used to have like an hour-long lecture about the amazing history of coal, and I wish we had time. The imperial moment, colonialism was driven by this, the industrial age, the first monopoly, the development of the modern economy, um, the history of labor, like the first strikes and the first humans replaced with labor and the first labor bust and the first time the military came in to break up a strike. The worst smog ever, the deadliest air quality event, today's worst air quality, the history of the railroads, the Western expansion, our interactions with Native Americans as we came west. All of this is tied to coal. So coal has a fascinating role in world and US history, but we're focusing on the AP test. So we're going to talk about coal formation and we're going to talk about coal quality. I think you've seen the slide before. Basically, organic material gets squeezed into coal. And the basics are that this is basically sedimentary. If you go really, really far, you can metamorphose this a little bit, meaning you can transform rock into a different rock type by adding more heat and pressure. This is made from swamp plants that died a long time ago and got squeezed. You know, they were transformed by heat and pressure, which is squeeze, into something else. You're adding more carbon bonds by bringing an outside source of energy, the heat and the pressure. We use this for heating. We use it for electricity. We'll explain how steam makes electricity soon. And it's used for other industrial purposes. You should know that. Making metals, concrete plants use this, whatever. I'll be talking about peat soon. And peat is this stuff that you can buy to put into dirt. Plants are vascular. They have tubes. So like you've got veins and arteries. Plants have phloem and xylem. They're tubes. Those tubes are made of a carbon compound called lignin. Probably worth knowing that. It's not on your slide. Lignin. That's the chemical compound. It's a carbon compound. You know, kind of like sugar is carbon-6. Lignin is, I think, carbon-6 also. But it's a different shape. And lignin, when you stick it together, makes these really rigid structures. That's what makes trees stand up. They're big tubes, like high rises of lignin. And when a plant dies and gets chewed on by an animal and gets squashed by rocks rolling, it becomes little pieces of lignin. That's what peat is. It's partially decomposed plant material. You find this at the bottom of swamps, at the bottom of wetlands. There's not a lot of stuff that can eat it. Lignin is really sturdy. There's very few decomposers that can eat it. So in sedimentary rock, lignin is actually like, I think it might be the most common organic compound found in rocks. So you've seen this. If that mostly plant material gets squeezed, you tend to get more coal. The plant material is the part that becomes the coal. So if you had pure plant material, you would get pure coal. And this diagram has a bunch of packed information, so I'd like to explain. You can always pause if you need to. That's why we do videos, but I'd like to explain. What you're seeing here is a deposit of peat that's being squeezed more and more over time. So as time passes, you're adding more and more sediment, which is making more and more pressure. The red arrows signify pressure. The more you squeeze this plant material, the more you're going to wring out water. Think about squeezing a wet t-shirt. The more you squeeze it, the more water comes out. So that's what the blue is. You can see that by adding more pressure, you're going to have less water because you're squeezing it harder. There's a complicated way to say this. We don't have time. When you squeeze out the water, you tend to wash out impurities. Because under heat and pressure, other chemicals found in coal will usually leave as the water leaves. You can kind of imagine a tea bag like getting squeezed by a spoon against the side of the mug. So as you're squeezing the coal, the water goes away, and so do the impurities. Water and impurities go together in this sense. And so basically, by squeezing out all the other stuff, all you're left with is more and more carbon content, which means you've got more and more energy potential, right? So that's what the E's are. Those are energy potential. So this all starts with peat, and then you squeeze it some more to get lignite, and then you squeeze it some more to get subbituminous coal, then you squeeze it more to get bituminous coal, and then you squeeze it more to get anthracite. There's a gazillion ways to talk about this. I kind of thought that this was better, but when you look on the internet, you can find other ways if you didn't like my explanation. This captures basically what I just said in other ways. Now, you have to know these terms. Peat is not really coal. It's just like the stuff that you find at the bottom of a wetland. And if you can dry it out, it's got energy because, you know, it's like shredded paper. Paper fiber is lignin. So paper is basically peat, I guess. Yeah, it's bleached peat. That's the same thing. This feels a lot like paper fiber. So I think I'm just going to go with that. Yeah. This is a deposit at the bottom of a wetland. It has heating value, like you can burn paper, you can burn peat. And this was like the first common fossil fuel worldwide. Like medieval period and stuff, pre-industrial times. Some parts of the world still use this as energy. You can heat with it, you can cook with it. You probably shouldn't use this as an energy source today because we need those wetlands for other stuff. But anyway, peat. If you squeeze it some, you get to lignite, which is the crumbliest, brownest, wettest, dirtiest, lowest energy type of coal. This is like horrible idea coal because it's almost all other stuff. 20 to 25% carbon. That means you're burning a whole bunch of stuff that isn't the carbon. And so this is, of course, the dirtiest. Subbituminous is like mid-grade coal. It tends to look a little blacker. This has pretty good heating value. It's a little bit drier, a little bit cleaner. It's fairly common globally. Bituminous is the good stuff. That's hard coal. It's very, very dense. This is still sedimentary rock. It's kind of flaky, but it's pretty hard to get those flakes apart. You can see it looks kind of metallic. This has very good heating value, very low water. As you get to the really good bituminous, that's actually like pretty sweet. You know, the 50 to 60% carbon range, that's the world's most common coal, heating electricity. Anthracite is the good stuff. Technically, this is not a sedimentary rock. You've given it so much heat and pressure that you now get unique properties. So this is no longer sedimentary. We call that metamorphic rock. It's kind of melted down to like a fluid at some point. So this has been squeezed to the point of being basically pure carbon, over 80% carbon. You can actually find anthracite. It's called mega anthracite, or I think meta anthracite. I don't remember. It's like super anthracite that's like 99% carbon. That's a lot of energy potential. When you light this stuff on fire, it gets really hot because there's nothing else. It's just breaking carbon bonds. This is very dry. It's definitely more pure, and it's very rare. Technically, you should know that people talk about clean coal technology. And what that is taking one of the dirtier types of coal and heating it up to the point where you make something like this. That's called coke, like the abbreviation for Coca-Cola or cocaine, coke. And that's basically a super heated coal. It's very dry. It's very pure. We call that clean coal. But I gotta warn you, you've been in this class long enough and you've been in this unit long enough, you realize, right, that there's a problem shift here. When we talk about clean coal, I think that's one of your study goals. You can take dirty coal, superheat it to make it cleaner. So at the point of combustion, that's very clean. But then what did you do with all of those dirty gases, and how did you get all that heat? This is what we call a problem shift. Since you're spending energy to heat up the dirty coal, this probably is not a systemically better solution. Like if you had to burn coal inside of a hospital, yeah, it should be cleaner coal. But you've probably made pollution elsewhere to generate your clean coal. So anthracite is really cool. And there was a moment back in the 80s and the 90s when everybody was like, oh, we'll just make anthracite. But of course, that was shifting the problem to someplace else, because by promoting coal to high quality coke, you've left behind other pollution in a different place. It's just a problem shift. So, interesting thing, our country has really old crust, and so we've got all sorts of sedimentary layers. And so good news, the US has a lot of coal. But if you remember what I was saying about quality, look at how little is anthracite. It's basically just Pennsylvania. And if you look at the United States, dang, most of that is lignite, subbituminous. There isn't even a lot of high quality bituminous. We have a lot of the dirtier coal. And it's dangerous to get. Maybe you've heard about coal mines collapsing and stuff. And you'll hear later in the course about how mines are a primary source of water pollution, and in America we really care about our fresh water. And when you go to the mountains, there's always rivers. So it's a really dirty thing to extract. It's hard to get it out of the ground in terms of human safety, and it's hard to get it out of the ground in terms of water pollution. Plus, when we burn it, our power plants are really old. You know, it's like trying to run a really old car. Like, they're just inefficient and they're clunky and they're super dirty. So why do we try so hard? I gotta tell you, there's really no way that anybody can mathematically, logically argue a future for coal. I just don't see it. It's just not personal preference, not policy. There's just no logical argument. All right. That's it for coal. There may be a couple terms left over. We'll leave them for the end of the unit, but otherwise I think we're also done with fossil fuels. Thank goodness, because I'm tired of fossil fuels, kids. I mean, I talk about this 3, 4, 5 times a day for like 20 years. And you just, whenever someone says fossil fuels, you got to be like, bro, what are we, come on, like just stop.